Okay, so let's start the seminar today. So we're all happy to have Antonello Scardicchio talking today about diffusion, subdiffusion, and many-body localization in disordered spin chain. So Antonello received his PhD in 2006 from MIT in the US, and then was for 3 years at Princeton University. And after that, since 2009, he is permanent staff at the ICTP and also staff member at CISA in Trieste in Italy. He has an impressive list of publications, and I believe recently his central interests are quantum many-body systems, non-ergodicity, and quantum computation. And so with this, I suggest to welcome our speaker and start the seminar.
Thank you very much. Thanks, Alexei, for the nice introduction. And thanks for the invitation, everybody. So as Alexei said, my main interest these days is ergodicity in quantum systems, in quantum many-body systems. And one, probably, I mean, the most interesting development in the field in the last, it's been more than 10 years now, but you know, it was slowly catching on at the beginning. And it's now definitely, you know, a hot topic. It's the topic of many-body localization. So I gather that all of you guys are familiar with dynamics of classical and quantum systems and topics related to that. Probably not all of you is familiar with the Anderson localization and many-body localization, which is its extension to interacting systems. So I will try to give a larger introduction for the benefit of you guys. So here is a list of people with whom I've collaborated over the years, and every now and then I will just quote some work made by these people, with or by these people. So, you know, I acknowledge all their invaluable contribution to whatever I'm going to say now. Okay, very good. So, okay, I have to click. Good. So, this is the summary of the talk. So, first of all, I'm going to tell you what's the effect of disorder on transport in quantum systems and what's the difference between classical systems and quantum systems with disorder, in particular with extreme disorder. And what is localization? And then, you know, this localization is Anderson localization. I think that Phil Anderson just passed a few months ago, a couple of months ago, actually, discovered in 1958, and that has been source of you know, discussion and work both in physics and math for 50 years now. And then I will go more in details and tell you about the nature of the phase that precedes. So a smaller disorder happens in one-dimensional systems that tend to be many-body localized. Why one dimension? Because most of what I'm going to tell you is going to be based on numerics, and numerics in 1D is much easier for various reasons. For reasons peculiar to quantum dynamics, because things like TBD, matrix product states, and these kind of things have a natural application in 1D. And the second reason is that, you know, the linear dimension and the volume, they are proportional to each other. But usually when you are in higher dimensions, the linear dimension gets exponentiated. It gets, you know, power. So the scaling is usually made with the linear dimension, means that we have much smaller system sizes. Okay, and then I will argue about the implications of the nature of the delocalized phase, in particular how the strange slow transport modes that there are there for the theory of the many-body localization transition. Okay, so quickly, so as you know, in a perfect crystal, transport is ballistic. Okay, momentum is a good quantum number where packets just translate at constant velocity of group velocity. But the perfect crystal is an abstraction. Okay? Disorder is everywhere. And typically, both in quantum and classical systems, when you add a little bit of disorder, suddenly ballistic motions goes into diffusion. Okay, your system is described much better by diffusion equation than by idealizing packets of particles moving with a definite group velocity. Okay, so if you have conduction electrons, disorder can be included in a semi-classical approximation in a Boltzmann equation for the distribution function for X and P. This is a phenomenological, semi-classical approximation that works extremely well. People in chemistry, in material science use it all the time. It works fine, perfect. Okay. You can use a Born approximation to compute the scattering rate for a particle to go to P to P prime, from P to P prime. And this is essentially Born approximation, Fermi-Golden rule, whatever you want, will give you some kind of Fourier transform of the disordered part of the potential squared. Semi-classical approximation means that the wavelength of the particles, the quantum wavelength of the particle is much smaller than the relevant wavelengths of the system, the relevant lengths of the system. And in the case of a diffusive motion, the only relevant not the only one, but the most important relevant length is the mean free path. Okay, so if the mean free path in units of the wavelength of the particle is very large, semi-classical approximation works fine, and we have diffusion. Okay, Einstein's relation tells us that conductivity is proportional to the diffusion coefficient. And again, as a semi-classical result, what happens is that when you decrease, going from left to right, the mean free path, when you increase the disorder, the diffusion coefficient and the conductivity just go down smoothly, monotonically, smoothly, asymptotically approach zero. Okay, this is the typical situation. In 1958, Anderson argued that for sufficiently strong disorder, so when the wavelength, the mean free path and the wavelength of the particle become comparable, things change. Okay, and so, for example, it was considering this model, which can be thought of describing electrons in impurity band in a semiconductor, in which the electron can hop from left to right, right to left, with a given hopping strength T. Okay, it's an amplitude. So you see, oh, this should be C dagger I plus 1, sorry. C dagger I plus 1, Ci, okay? And so this can jump from left to right, or in general on a lattice, from one vertex to neighboring vertices on a lattice. And the energy on site for this thing is a random number. You can think of Gaussian distribution, uniform distribution, doesn't really matter much. And the range of this disorder is minus W to W. Okay, so changing the ratio T over W, which is a dimensionless quantity, it's like changing lambda over L mean free path. Okay, and Anderson showed that there is a phase transition. Okay, what does it mean? It means that while your semi-classical approximation, which works well at small disorder, describes a monotonically decreasing conductivity of the diffusion coefficient, the real quantum calculation, once the conductivity, this should be the dimensionless conductance, but bear with me for a second. When the conductivity is proportional to a quantum of conductivity, okay, then it suddenly drops to 0. And then it stays exactly 0 for any disorder larger than that. Okay, this is very peculiar. It's very interesting. It's a purely quantum effect. There's nothing classical about it. Okay, if you send h bar to 0, this thing just disappears. Actually, this point just goes to infinity, if you want. Good. Okay, this thing has been has been verified in many things. For example, in semiconductors, you see here the conductivity. Look at the right part of this thing here. The conductivity goes to 0 when this, this. You can look at the. So in experiments, you cannot change the disorder. Okay. So what do? You change the opping. How do you change the opping? Opping is given by the overlap of the wave of the lobes of the orbitals on a given atom. Okay. So if you want to increase the overlap, what do? You squeeze your system, so apply a pressure. Okay. And therefore the two orbitals overlap more, and the integral, which is T, which is the opping thing, increases. Okay. So when you decrease, this go away, T goes down, and you get a transition. Okay. This has been verified also by imaging the wave function in cold atoms in optical lattices. Okay. And this is the image of wave function. And as you see, the wave function has this exponential profile. And this exponential profile means that the nature of the eigenstates of your system, they are completely different from Bloch waves. So we are at the opposite extreme from a crystal ballistic. So I think there is some work going on outside my window. So let me close the windows. The air conditioning is off, so I will. The window was open to let me breathe, but I mean, if there is too much noise, it's better than I die that you don't hear what I say. Okay, so Anderson localization brought up a huge body of theoretical and mathematical work, beautiful mathematical work on random Schrödinger operators. A lot of mathematical physicists work on this. Very nice. Unfortunately, nobody has ever proved that there is a transition in finite dimensions. The only proof that there is a transition we have is on the Bethe lattice. For all mathematicians were able to prove that there is a localized phase, but not that there is a delocalized phase. So I guess for a mathematical physicist, if you want, Anderson localization is everything that you can actually prove. You cannot prove diffusion in some sense, in these systems. Okay. All right. So, but electrons have a charge, and they tend to repel each other. In particular, they tend to interact with each other. Okay. So it's not just electrons in a background potential. Of course, Anderson knew this, and the question was already asked in his paper at the beginning. He said, okay, electrons will certainly, they will have a charge. Okay, it will be screened by plasma effects, this kind of things. But, nonetheless, they will interact. For the moment, in order to do some progress, we will neglect this interaction. But this interaction is there. And this was a big problem over the years because people kept saying, I wasn't active during those years. I mean, I was in elementary school, but I went back and read the various papers, and there were essentially two schools of thought. Okay, one that would say, okay, Anderson localization is nice, but doesn't really exist. As soon as you introduce interactions, there will be a tiny conductivity, which probably is not measurable. But it's there and it's not zero. And another school of thought was like, no, really the conductivity is really zero. Zero as for a theoretical physicist is zero. The Anderson localized phase is stable upon the introduction of an interaction. So this thing went on and on for years, and until a seminal paper by Bascal and Nature in 2006 put studying perturbation theory in the interaction in what now we call a proper way. They were able to show that perturbation theory is stable upon the introduction of the interaction, and therefore the phase really, the conductivity really remains zero. A lot of paper after that, I mean, this paper didn't, I mean, this paper, the 2006 Annals of Physics paper by Basco and Ranchuler is 60 pages of diagrams and stuff. So I mean, it's not the kind of paper that makes an impact right away, right? So there was a lot of people working on that, digesting that, doing numerics on that. There is no numerics in that paper. So, you know, now people are easier convinced if you show them a graph made with Mathematica than if you show them 50 pages of diagrams, unfortunately, if I can say. And so now the thing that started with Basco and Ranchuler is now called many-body localization, and it's you know, at the basis of our understanding of ergodicity in disorder, ergodicity breakdown in disordered quantum systems. This figure was taken by Basco and Ranchuler. It's taken by Basco and Ranchuler. So what happens? So they don't show things as a function of disorder, because as I told you, in experiments, you don't change disorder. Okay, but in a many-body system, you can change temperature. And so if you have an the interaction is lambda. The interaction, the dimensionless interaction strength between the electrons is lambda. Delta zeta is the energy scale of the following thing. You take, so all the single particle wave functions without interactions, the single particle wave functions, they are localized. They have a localization length which is of order zeta. Now, if you take a box made of this zeta and you ask what's the gap inside this box, it's just a construction. This is this delta zeta. So you see it's h bar squared divided by m times L squared, zeta squared. Okay. So zeta in one dimension is inversely proportional to w squared. There should be a t here, so it should be like something like t squared over w squared. So in perturbation theory, they were able to prove that if the lambda is smaller than delta zeta divided by temperature log of temperature divided by delta zeta, then the system is really an insulator, that sigma is zero. And then there is a critical temperature, because as I said, you cannot change the disorder, you change the temperature. And then something happens. It's not clear what happens close by to the transition, not even in perturbation theory, and then it goes up until, you know, you get to a fully developed matter. Okay, good. What kind of perturbation theory do they have in mind? This is what I'm going to show you is essentially an interpretation that of their calculation that it's a pictorial interpretation of the calculation that helped us a lot to work on defining the local integrals of motions that I'll tell you about. Oh, by the way, if there is any question, you can stop me anytime. I know I'm going over many minutes.
Antonello, sorry, this is Victor. I wanted to ask, what is the dimensions of a system?
Okay. So in Basco and Ranchuler, the dimension is arbitrary, any d.
So
okay?
So what about? So it means that even in 3 dimensions there is no conducting state.
Yes. So in 3 dimensions, if the disorder is sufficiently large, you have all states are localized, right? I'm talking about a lattice.
Ah, so we're talking about a large disorder. Okay, okay.
We're talking about a lattice. Yes. Sorry. So you take the Anderson model on a lattice in 3D. You take disorder larger than in 3 dimensions, like disorder for uniform distribution has to be larger than 16 times the hopping, and then all the wave functions are localized. Then you introduce interaction.
Okay, good.
It is very important because people actually, I mean, we have Basco and Ranchuler, which is and our work with Markus Müller and Valentina Ross, in which dimension is arbitrary. D is a parameter, okay, but it's perturbation theory. We have numerics in 1 dimension, and people have been claiming that you know, non-perturbative effects in 2 dimensions and higher will play a significant role and destroy this MBL things. But I will discuss about this later. we don't know the answer to that question. Okay. So essentially, what does it mean to transport?
If I may just ask also, Antonello, if I remember correctly, the three of them just assumed that all the single particle eigenstates are localized. That's it. And how
That's
you
correct.
do that is your business, so to say. But once you have that, so they don't mix in states which are delocalized. They only have single states which are localized.
Yes.
Maybe within a finite upper bound to the localization length. That I don't remember whether they require that. But maybe you can comment on that, please.
No, they actually, you are right. The assumption in their work is that let's take an Anderson model in D dimension for without interaction, all the states are localized. So this order is sufficiently large. Okay. Then actually what they do, they chop their system into the quantum dots of size zeta, the localization length. Okay. And these boxes here are their quantum dots. So there are a few particles per quantum dot. And then essentially they do the Altshuler, Kamenev, Geffen, Levitov construction for every quantum dot. And then they merge the different quantum dots, allowing for particles to not to jump from one dot to the other, but to interact with the particle in the next dot. But all the single particle states have to be localized. Even with this assumption, some people have problems in 2 dimensions. Okay. 2 dimensions. Okay, so what does it mean to transport something? It means that I do something on the left, and then eventually at large time, so in resonance, something happens to the right. So for example, I move this particle up here, and then this costs me some energy. I'm not in resonance. So what do? Well, I mean, this next particle is interacting with this one here. So I can have this process in which this particle loses a little bit of energy. But you see, this gap is larger than this. So I still have some energy to get rid of. So maybe I can do something farther away or in the same dot. Okay, so this goes down. And now this is a little bit larger than this gap here. And then maybe I can move something here. So I have a sort of avalanche. Okay, I make a small thing here, and then I see if this perturbation can move. Every time I move away, I get an interaction. I get a matrix element which is proportional to the interaction. And the denominator is proportional to the change, the product of the changes of the energies over all the steps. So what I need to do is, this is a random number, because lambda is just a number, but this down here is a random number. You see, every quantum dot has its own spectrum, which is random. It depends on the local structure of the quantum dot. So I have to study the probability distribution of this random number when I take L to infinity, because I want transport. I don't want things to be localized. So we have to look at the absence of resonant processes. We want that the probability distribution, the probability that the amplitude of a large process is, the probability that this amplitude is non-zero goes to 0. Okay? Actually, in perturbation theory, you can show that there is an envelope for sufficiently small lambda. There is an exponential envelope that you can put such that the probability that the amplitude is above this exponential envelope is 0. Okay, look at this. The probability that the amplitude is above is 0. That it's below, it's 1. For every point from a given point of order 1 to infinity. So if you have this, transport is inhibited. In a summary, this is what Bascom and Altshuler did, different ways, and with many, many caveats. We require 2 seminars just to discuss about this paper. This is also what we did in our paper in Nuclear Physics B with Valentina Ross, my former student, Markus Müller, former colleague, former at ICTP, now is in Switzerland. in 2015. And it's also at the core of what John Imbri did in his Journal of Statistical Physics paper for a different model, a one-dimensional model, not the one we have, one without conservation numbers.
Antonello?
Yes.
Sorry, we have a question from Igor.
Yes.
Hello. So could you please repeat, what is this index L or X in A? What is this length?
How do I go back? Sorry, how do I go back here? Sorry. Do you know how do I go back? Okay,
left arrow?
Yep, there we go.
Yeah, no, the left arrow was giving me some, I had to click on the thing first. Okay, so it's the, so we have an amplitude. Technically speaking, this is an operator, okay? This process is described by an operator, which has C dagger, C dagger, C dagger, C, 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 okay?
Mm-hmm.
Destroys a particle here, it is there. Technically speaking, L is the length of this operator.
I see. And is there any particular reason why you consider triplets of these energy splittings? Why 3?
Oh no, 3 is because I did 3 processes. If you have 4, if you have a 4th box, you have a 4th delta E4.
I see.
This is so you, in the denominator, you have a sum, you have the largest denominator as the sum of L of these things, if you consider processes which go up to distance L.
I see, thank you.
You're welcome. So this 3 just comes from the fact that I stopped at 3 boxes here. So when this happens, what are the consequences? Consequences are absence of transport, emergence of local integrals of motions. And actually, local integrals of motion explain everything else of the phenomenology of MBL. Local integrals of motions are local operators. Okay, these operators with many C's and C daggers, but they get an exponential envelope. So the probability that you find an operator C35, C dagger 35, C1, it's e to the minus 35 divided by Z. Okay, so that's why they're called local. They're not really local in the sense that they contain all, that you have to put all possible operators in, but if you truncate them at a given length, the error that you make is exponentially small in this length. Maybe we should have called them quasi-local. So if you have these local integrals of motion, then you have violation of eigenstate thermalization hypothesis that for our purposes, just the eigenstates are not equivalent to the microcanonical ensemble. You have area law entanglement at high temperature. We are used at area law entanglement for ground states, but as soon as you go up in the spectrum, you go finite temperature, typically it's volume law. You have a memory of initial states in local observables that you don't have if you have ergodicity. Then if you look at the spectrum, the gaps of the spectrum are distributed like Poisson and not like Wigner-Dyson, as it is usual in a chaotic quantum system. And then you have the slow growth of entanglement. The entanglement grows logarithmically with time and not linear with time, like in chaotic systems. Okay. Good.
Antonello, I have a question,
yes.
Probably jumping ahead of what you will talk about. So what's the fate of these quasi-local integrals of motion once you cross over into the metallic regime of this many-body interacting system? Will they still stay integrals, but they just change somehow, or what can you say about that?
So this is a very good question, because the only thing I can tell you is that the perturbation theory breaks down. So I have a perturbation theory construction for these integrals of motion and will not converge. Okay. Now there are different scenarios, and we were never able to prove which one is correct. Either they all die altogether. There are no local integrals of motions anymore, and the integrals of motion become non-local, and essentially they become projectors over eigenstates, if you want, which makes not, I mean, they are not useful at all, because this is a many-body system. So these are operators that you can never measure in an experiment. These will become operators. Or some of them die and some of them don't. Because remember that if there is a mobility edge, I mean, if the interaction becomes sufficiently large, but the temperature becomes sufficiently small, you will always be localized, back to localized. So is there an operator that it can be attached to these things?
Yeah, but I mean, what you change is essentially only the energy of the states, right? So you don't change the Hamiltonian. Or you can, let's say, you can cross from the localized to the metallic phase by just changing energies and not the Hamiltonian. So if they are integrals of motion, they should stay integrals of motion because you didn't change the Hamiltonian. So I always have problems here at this.
Let me actually, let me go to this next page and answer your question, okay? I will answer your question on this page because I need this graph.
Okay, thank you.
Okay, so this is numerics done by many people, but the first and best was that by Fabien Allais, published in 2015 on PRB. Takes interacting spinless fermions, so the same model that I told you before with nearest neighbor interaction. So you see now there is C dagger I, Ci plus 1. So this part is the Anderson model, this part is a little bit of, this part is interaction is set to 1. If you go to if you Jordan-Wigler this in one dimension, you get the spin chain, Heisenberg spin chain with random fields. And this is what everybody has been looking at. Now, look at this line here, okay? This line here, which is the rightmost point of this ergodic phase, is, so if you go to the right of this is the entire spectrum. This epsilon is just, you know, with which fraction of energy you are, between 0 and 100%. So this is the entire spectrum. So if you are to the right of this point, all the states are MBL, are localized. And integrals of motions exist. Now, if we reduce this order, we enter in this region in which at low energy and a very high energy and low energy, you have localized states, but in the middle you have delocalized states. So the question that Sergey asked is, what up, if I understand it correctly, is what happens to integrals of motions here? And the question, and the answer is, I don't know. Because I don't know how to attach an operator to a state. What I can do, we try to do that, is to do perturbation theory constraining with projectors over a part of the spectrum. Okay, but this is difficult to do because the spectrum changes with when you change the disorder. So how can I write, if I can write a projector of a part of a spectrum, I've diagonalized the Hamiltonian. So you have to write somehow some kind of projector which only depends on the disorder part of the Hamiltonian. So we could never, so what I can tell you is that local integrals of motions exist all the way down here. From this point here down, some people believe that some local integrals of motion will exist, some will be non-local, and some people believe that none of them will exist. Personally,
and are there also some people who think that there are no integrals of motion in the right part of the plot where you say it's all MBL? So in principle, you could actually, so what are the opinions there? Because to me, it sounds like maybe they also only approximate there, but maybe, you know, exponentially close to something reasonable, the deeper you dive into this MBL phase, so to say.
Well, some people don't believe this MBL phase exists for this model, actually. And this I will show you to you later on. So if the MBL does not exist, the integrals of motion do not exist. What we did is, to be precise, to state exactly what we did was, we worked within the same approximation of the original Bascal and Schuller paper. And we showed that with those approximations, local integrals of motions exist. Okay. But again, they were doing approximations and they were doing perturbation theory. One of the two things can fail. If perturbation theory fails, it's not guaranteed that there are no integrals of motion. Like in the Anderson model, if the locator expansion fails, you still can have localized states. It's just locator expansion failed. In fact, the locator expansion overestimates the disorder, even on the beta lattice. Okay, the locator expansion will give you a transition beta lattice with connectivity 3, which is, I don't remember, something like about 40. Well, the true transition is 18. So locator expansion is this kind of perturbation theory that I was doing.
Antonello, we have
Yes.
a question.
Yes.
From Igor.
Another question about these local integrals of motion. What is the number scale with the system size? Do they follow Hilbert space size or linear?
No. They are one per spin.
Interesting.
This
So
is very important. This is very important because they can then you can use them as some kind of renormalized sigma z things to label your eigenstate. There is
the number of eigenstates is exponential.
Q to the n, exactly. So a local integral of motion can be as eigenvalues either 0 or 1. Okay, so you just need n of them, and then you can span 2 to the n eigenstates, which are the bit strings made with 0 and 1s. So every eigenstate is labeled by you have to think of them as renormalized SZ operators in a spin chain.
I see. So in a way, you need all the set to kind of integrate the system.
Yes, but only L of them. As you said,
that's
2 to the L.
That's surprising because generally for many body
I completely agree.
chain,
It's not true for general many body systems. It's only true for these models in the MBL phase. It's not true for these models in the ergodic phase.
I see. Okay, thank you.
And once again, this is for 3 dimensions. This is paper.
These numerics is for 1 dimension. The paper on perturbation theory is arbitrary dimensions, but it's perturbation theory.
But this graph with ergodic states is for 1 dimension.
1 dimension. Look, this here is sum over I plus 1. So it's a chain.
Yeah, but just a second. Ergodic in some sense means extended states, yeah? Or not?
No. You don't look at the states. So how do you define? You don't look at. It doesn't for a many body state doesn't mean anything to say extended. Like it's not single particle state. So what you look at measures of ergodicity. For example, you look at the spectrum here, and you compute this observable of the spectrum. Okay, which is take an eigenstate, you take the before and after, you look at the gaps, and then you take the ratio of the minimum gap divided by the maximum gap. If this is 0.39, this is 0.39 for Poisson distribution, and 0.53 for GOE. As you see, as you increase the disorder, this goes from GOE down to Poisson. Okay, and you have some sort of crossing which moves actually a little bit. This is something that we need to discuss. It moves a little bit with the system size. If you try to do finite size scaling, assuming that you are in a critical region here, you get critical exponent which are smaller than 1, and disorder which is 3.7. That if you see is more or less here. So this is spin chain 1D with disorder. Okay, you have to look at various things. You can look at the entanglement of a single eigenstate, whether it's volume law or area law. The spectral statistics. Then we looked at something, the memory of initial conditions. We start with initial condition. We start with systems which is a little bit more polarized, a site which is more polarized up than down. Then you see if at infinite temperature the states evolves. But let me show you. So this is integration of the Schrödinger equation for a chain of 14 sites. And this is the energy density. The energy density is just the expectation value of the Schrödinger equation of one of the terms in the sum of this thing, okay, for every x. So for small disorder, here the disorder was something around 1, okay? This is the same model as here. For small disorder, let's look what happens. So you start with an initial state which has a big imbalance, and then it goes down. Actually, this follows pretty well the diffusion equation. And you can also extract the diffusion coefficient for the energy here. And if you keep going, so you see this actually went from this, you know, and then you have the largest wavelength surviving, and then this dies exponentially. And the exponential is related to d. Okay. It's d k squared. And then it stays like this. This is equilibrium. Then I can let the movie go on, and it will stay like this. The energy will just fluctuate a little bit. And this is perfectly good microcanonical equilibrium. The entire energy that was at the beginning was, you know, was most here and less here. It's now equipartite. Now let's increase the disorder. Same system, same observable. Let's increase the disorder. Let's see what happens. You start with the initial state, which is very similar to that one. You cannot do it exactly equal. It's because the Hamiltonian is different, the numbers of it. Okay, but you have the same imbalance, and then you let the system move. And this is it. For 14 sites, you can take the diagonal ensemble and show that this imbalance is never going away. And this just goes on and on. So the system is energy is localized. It's localized here, and it's not transported to the cold part. This is the hot part, this is the cold part. It's not transported. So there is no diffusion equation. Okay. Let me reiterate. This is a non-integrable many-body model. Okay, so there are no, this is not, forget the fact that this is Heisenberg. There's no thermodynamic Bethe ansatz or Bethe ansatz that you can solve, you can use to solve this.
Sorry, Antonello, what do you mean by non-integrable? Although it
non-integrable in the sense of Bethe ansatz integrability.
Well, I mean, you tell us, you teach us that it has integrals of motion, and then you tell us it is non-integrable.
You're right. These are local integrals of motion that they don't come from algebraic properties of the.
Well, who cares where they come from? As long as they are there, I could say, great, it's integrable, right? Or,
right. Okay, it is integrable in this sense. It's not integrable. So sorry, maybe I'm confusing the question here. Some people see the Heisenberg chain here and say, oh, this is integrable. No, it's not. Because if I add the small disorder here, then I go to this. Okay? If the disorder is larger, then these integrals of motions arise. And you get this. Okay? All right. Now, let me describe, okay, in the last 10 minutes, the more modern, I mean, this is all things back to 2015, 16. The last years, what we have been doing is trying to understand, okay, take this data and do finite size scaling. You get a collapse with nu, which is less than 1. This is true for everything you take. Every data, I'm just using the Fabienne Alet's data from 2015, but all the data that has been produced by hundreds of papers on this model, numerics and stuff, they all give critical exponents which are less than 1. This is a problem. This is a problem because one old nice paper by Chase, Fisher, and Spencer, which was interpreted by Anusha Chandra and Chris Lauman and Vadim Oganessian in 2016, showing that the critical exponent for this disorder, for a disordered system, this kind of disordered system, should be larger than 2 over d. And for d equal 1, this means it should be larger than 2. This is not the only problem with this data. there is another kind of problem. Then the problem is that the crossing point is actually flowing. And these are connected, because if the critical exponent is small, it's essentially telling you that you see little curvature in your data. And so, you know, if you impose that you have this length has to diverge somewhere, then it has to diverge pretty quickly. It means that the critical exponent is small. Okay. Good. Let me show you another way of seeing this problem from another thing. So you probably have heard about, if you haven't heard about eigenstate thermalization hypothesis, essentially it poses that the expectation value over eigenstates of, it's a bootstrap of the idea that a single particle, that random matrix describes well chaos for the Schrödinger equation of a particle in a billiard. Okay, so in a many-body system, you have to be careful a little bit about discussing about the things that change with the energy, but more or less, essentially, it says that for eigenstates close to each other, and you have many because the gap is exponentially small, the off-diagonal elements of local operators are random matrices, GOE random matrices in this case. If it's a GOE random matrix, then I can compute the Binder cumulant. The Binder cumulant is 1 if this thing is a Gaussian. It's not 1 if it's not a Gaussian. Okay. And so what we did is we computed in this paper with Rajat Panda, Maximilian Schulz, Scott Taylor, and Marco Znidarich, we did hexagonalization of systems up to 22 sites. Every color is a fixed disorder, value of disorder. Every point is average over thousands of disorder distributions. And you compute a Binder cumulant. You see, this is 1, this is logarithmic scale, this is 1. And what happens if the disorder is small, this stays 1. If the disorder keeps increasing a little bit, this goes away from 1, but then as a maximum and goes back to 1 for sufficiently large system size. And this keeps doing and doing it. And essentially, the important length scale is the position of this maximum. After this maximum, the system realizes that it's actually ergodic and not localized. And the Binder cumulant starts decreasing and going down. So if there is an MBL transition, the position of this maximum must go to infinity for a finite value of disorder. Okay? So now this disorder, the maximum disorder here is 2.6. It is not the 3.7 that we have in the data. But let me, bear with me for a second, and let me show you. If I look at the position of the maximum L0 as a function of disorder W, you see this thing is just growing linearly. Maybe there is a little bit of curvature, maybe not. And this, if you look at the median or the average, these are distributions, as I said. So if it's ETH, this curve looks like this. If it's MBL, there is no such maximum. So this curve just looks like growing. Actually growing in logarithmic log linear scale because it has to grow exponentially. But you see, if I look at this data, there is no signature of a phase transition yet. We are too far away. Okay, this is perfectly well fit by a line. If you want. So some people have looked at this data and similar data and have proposed that there is no transition in this MBL model. And these people, by these people, I mean people of the Thomas Prosen group in Ljubljana. This was also based on things that these non-perturbative effects that were identified, quote unquote, though not put on a sufficiently firm ground for my personal opinion, by the Delocalized veneers. We don't think this is the answer. Okay. We think that the question is that the transition is very peculiar because the localized phase is very peculiar. The delocalized phase is very peculiar. It's not like in the Anderson model. You go from diffusive to localized. There is something in between. And this something, so in the Anderson model, you go from the diffusion coefficient goes to 0 and stays 0. But when the conductivity is 0, it's not, so I can look at the current, okay? And if there is a conductivity, the current decreases like 1 over the system size for fixed voltage, delta V. Okay, I'm talking about 1 dimension, sorry, just 1 dimension. But when the conductivity is 0, maybe it's not because this coefficient, sorry, when the conductivity is 0, maybe it's because the current scales like L to the minus gamma, with gamma larger than 1, and not like E to the minus L, like in an Anderson localized model. Now, this is not being observed in the Anderson model in any finite dimension. Maybe in the beta lattice it has been observed, but not in the infinite dimension. So one can have non-ohmic subdiffusive dynamics. And in fact, this is what is observed in this model. What is observed in this model is that if you look at the resistance, and now I'll show you how to define the resistance, this grows like L to the gamma, and gamma is 1 up to a certain point, a disorder which is much smaller than 3.7, is actually 0.5, and then starts growing and probably diverges at a given point. So if you want to interpret this part as diffusive, I mean, this part is not diffusive, is not localized, it's subdiffusive. Now let me show you. This so in a couple of papers, there were a paper by Marko Znidaric, myself, and VP in Varma, in which we showed this diffusion. The subdiffusive part was shown in another paper by David Gruitsev, Yevgeny Barlev, looking at eigenstates. So what did we do? Remember, so this diffusion-subdiffusion transition is at 0.5 disorder, and the transition to MBL was between like 4, and actually, if you are careful with the data, it could be even 8. Okay. So let me skip on this because I'm running out of time. So let me show you how we found this transition. So we considered open system. So take this Heisenberg chain and put it and open it on the boundary, only on the boundary. So we have particle injection here and particle extraction here. Okay. The system flows to infinite temperature. There is no control on the temperature of the baths. But it doesn't matter because MBL is a transition at infinite temperature in 1D. And so we look at the non-equilibrium steady state in this setup. Now, the good thing about the open system in this setup is that we can go to huge system sizes for which we cannot do exact diagonalization because we can do an analog of MPS, which is called TEBD. Okay, so we could go to very large system sizes, finding the non-equilibrium steady state. Okay, the non-equilibrium steady state will be close to infinite temperature, but it's the distance from this infinite temperature state, which is just the identity, which has all the information. Then we look at the current, and then we look at how this current scales with system size. These are the data. Now look at the system sizes we could reach, 400. Okay. At small disorder, we get the current as a function of disorder, as a function of length, which after an initial transient goes to slope 1. Without disorder, we have slope square root of L, which is not ballistic. Ballistic will be L to the 0. It's not ballistic, and it's due to a peculiarity of the Heisenberg model. The Heisenberg model is integrable, but integrable in the Bethe-Ansatz integrable sense. And the transition and the and the transport is not ballistic. It's super diffuse, distributed to terms. This is a finite size scaling, and you see that the length that constrains the finite size scaling is h to the minus 1.33. This is from numerics, and this you can understand it quite clearly. But I'll tell you later, because I want you to show this thing here. So there is all these black numbers here. The slope is going to be 1 over L. This is a log-log plot. Okay, slope is going to be 1 over L. If you increase the disorder, however, the slope changes continuously. And for h equal 2, for example, you see it goes after a little transient, it goes straight on this straight line, which has a slope which is 2 or something. Okay, we haven't put it in here, but it's much, you see, it's definitely much larger than this one. Okay. Okay, so we can understand this h to the 1.33, which is essentially the mean free path calculated from the Fermi golden rule for the Heisenberg magnons. Okay, it's 4/3. Anyway, and if you plot this gamma is 1, 1, 1, and then starts detaching and growing. We could not get to 3.7. Again, conservation of difficulty, if you want. And this numerics helps us a lot for small disorder, but when you approach higher disorder, why? Because this current is too small. The current is too small. Essentially, well, it's not too much the fact that the current is too small. It's the fact that we have to find the non-equilibrium steady state. So how fast this algorithm goes is dominated by the first gap in the Lindbladian spectrum, and this also shrinks to 0 and shrinks like L to the minus gamma. So the larger gamma, the smaller the gap, the slower the algorithm. So we cannot go to large disorder because of this reason. So so this gamma is, you know, the diffusive phase ends at W, which is equal to 0.5. So if we really want, and this is also the resistance. The resistance is the inverse of the current in this case. So also with the resistance, we find the different things. R goes L to the gamma, and you find it goes like that. We have distributions of resistances, but I will skip on this. Okay. The question is, where in the Basco-Lennard-Schur diagram is this region? Is it in this part which is not approachable by perturbation theory somehow? Or is it in this part, and this thing has been overestimated by the usual arguments of locator expansion and overestimating the transition? And so the question now, whether the transition in this model exists or not, would be translated into the proposal 0 says that this gamma just grows and grows. So the system is always subdiffusive, never MBL. Okay. Or the transition or the gamma diverges at a given point. And then the system exits the subdiffusive phase and enters the MBL. But if we were expecting to do a localized to diffusive transition, to see a localized to diffusive transition as in the any Anderson model in finite dimension, this is out of the window. The diffusive phase is much earlier than whatever purported MBL transition there is. Okay. So I really think this understanding this subdiffusive phase and the open system dynamics is the best suited thing to understand this thing here. Is the core of understanding why we have not pinned down the MBL transition yet. These are the conclusions, and I'm 3 minutes over time, so I will leave the conclusion up and stop here.
So thank you, Antonello, for your lovely talk. And we are open for questions.
Okay, you have just shown the Altshuler paper picture with graph with temperature, but the results you present are, I guess, at 0 temperature, yeah? Or,
no, they are infinite temperature.
Ah, so, okay. So this explains how you have a delocalized state in 1 dimension, or I mean, you start.
Exactly.
Okay. Okay.
Yes.
Now.
At 0 temperature, you're right. Actually, if you look at this thing here, look at this thing here. This is the fraction of the energy. If you're at 0 temperature, you're on this line here, and this line here, this curve becomes tangent and really goes here. All the states at 0 temperature are always localized. I mean, the ground state and the first excited states are localized.
Okay, technical question: how do you introduce temperature in this in your calculations? Just
okay. So technical answer is the Lagrange multiplier to go from the energy to the from the microcanonical to the canonical. So it's the derivative of the entropy at that point, at the point in energy. Okay. Clearly, if it's not ergodic, it doesn't make sense to talk about temperature.
Okay, thanks.
Antonello, what do you mean by the ground state is localized? I mean, you have
yeah, you're right. I mean, the ground state is the ground state, right? So excitations on top of the ground states are localized. Take the ground state, flip a spin, this is not going anywhere, because essentially the ground state will be some kind of selections of magnons, few magnons, and this will be localized. So when you turn on when I'm talking about this, Bascom and Altshuler in their paper, they set up the problem really nicely. They say, I take an eigenstate, I apply either the current or some spin flip operator, okay, and then evolve and look, and then reabsorb the spin flip far away, okay. Then do I have transport here? So the idea is always I take an eigenstate, I do something on this eigenstate, then what happens to this something?
So this spin model in 1 dimension, which you discussed here, is probably the simplest model one can perhaps come up with. And it sounds like it is still not, so to say, there are still different opinions on what's going on there, right? Isn't it quite surprising? I mean, so are there maybe simpler models one can come up with in order to somehow clarify some of these issues, or can you comment on that, please?
So this model is as nearest neighboring interaction. As soon as you decide, any other model will have either next to nearest neighbor hopping or next to nearest neighbor interaction, thereby effectively reducing the length of your system by half. Okay, because now the lattice spacing is not 1, it's 2, morally speaking. And these are already small systems. The largest systems anybody could tackle is 22, 24 for exact diagonalization. For transport and on equilibrium steady states, we could do the open system dynamics. We could go up to 400, but at small disorder. Again, if you go to large disorder, you are limited. So for example, for disorder equal 2, we were limited up to 12. I mean, so changing the model necessarily reduces the effective size of your system. And this makes the problems, the finite size scaling worse. People have studied next to nearest neighbor hopping, next to nearest neighbor interaction. Next to linear stable wrapping is the good thing that it's not integrable even without disorder. It's not Bethe-Hans, it's not the Heisenberg model. Okay. So so you expect diffusion already without disorder. But again, the finite set scaling is worse than this thing, even without disorder. So it's a problem. It's a problem of having to define these properties in terms of eigenstates. If you don't define these problems in terms of eigenstates, or if you really don't need to evolve the full Schrödinger equation, then things might be better.
Mm-hmm. Thank you.
One more question. When you're saying the infinite temperature or even finite temperature, how do you still preserve quantum properties of the system? I mean, it should become classical in some sense.
And this is the beauty of MBL. The system does not become classical, even at infinite temperature.
Okay.
And this is inherited by the Anderson model. The Anderson model in the mid, I mean, if you on a lattice, if you go, if you go at in the middle of the spectrum, you can have all the states localized. So the semi-classical, sorry, the classical limit is based on the semi-classical limit, and the semi-classical limit collides with the Anderson localization. So if you really send H bar to 0, then you don't have any Anderson localization, everything goes back to classical. But as soon as you have a H bar finite, even if you go at infinite temperature in some models, like lattice models, you don't find the classical limit.
Okay.
Okay. Any more questions from the audience?
Yeah, I have a question. So you mentioned that there's some statement that the critical exponent of transition for localization should be not smaller than something. Could you please explain a bit what is the larger? Yeah,
so this is based on, they have to be larger than 2/d. And this is actually satisfied by all disordered systems that I know of. For example, if you have fully connected system, you put D to infinity, this doesn't tell you anything, it says nu has to be larger than 1. If you look at the Anderson models, in 1 dimension, there is no transition, okay? In 2 dimension, there is no transition. In 3 dimension, for the GOE ensemble. In 3 dimensions, you get this has to be larger than 2/3, and we know that it is. So this is a paper by Chase, Fisher, and Spencer in 86, which is actually, I haven't reread it in a long time, but the argument is pretty simple and it's pretty robust. It's based on the definition of the order parameter as average over disorder, and you want that this thing is. There are some questions about the order parameter existing as an average, so the average has to be much larger than the variance, and this puts some limitations on the critical response. I'm sorry, I cannot tell you much more about this because I don't remember. But really, I mean, if you look at the paper, it's like 3 pages, not even 4 pages, if I remember correctly, and the argument is crystal clear.
I see. Thank you.
And this paper by Chandran, Lauman, and Oganessian is unpublished. It's on the archive. Is essentially saying, look, guys, there is this paper by Spencer, by Chase, Fisher, and Spencer, and if you apply this to MBL, it works because all the conditions are satisfied, and tells you that the transition, if there is the transition in 1 dimension, has to be nu larger than 2. I haven't talked about all the theories of the critical point based on the Kosterlitz-Thouless scaling, which would give nu equal infinity, alla Kosterlitz-Thouless, so non-analytic divergence. They, of course, do not agree with nu less than 1, and they cannot be used, frankly, to explain this data. Maybe this data is just, their system sizes are too small to see the true critical exponents. Maybe there is no transition.
I see.
Okay. And
Okay.
so, are there any more questions from the audience?
Yeah, I have
I
another.
this one. Okay.
This looks like a lot of numerical efforts over the last whatever 10 or 15 years, so can you maybe just maybe also quite some analytical progress, maybe a bit slower, but still. So what would be what's the future? What do you think? What's the perspectives which you see here?
So I am very much interested. I can tell you what I'm interested in. So I'm very much interested in the applications of these ideas to, which was the original reason why I started looking at these things, to quantum technologies. So as you know, there's been a lot of work over the years making parallels between the behaviors of the thermodynamics of spin glasses and the behavior of algorithms that try to solve NP-complete problems. Now that we have some prototype, small and ugly quantum computers, we might ask what are the phenomena that slow quantum dynamics that might be important for understanding which quantum algorithms are doomed to fail, and which can actually give us a speed up over classical algorithm. So it's so this is one of the applications in some sense. I mean, there are a lot of things which are not clear, but it's clear that this phase is there. Maybe it's there only in perturbation theory. There are non-perturbative effects that turn the conductivity or whatever it is that dominates the dynamics from being, you know, exactly zero to being 10 to the minus 20. That it's not going to matter for you know for deciding whether an algorithm is slow or not. So this is one of the things that I'm interested in. The field by itself has a lot of unanswered questions, and as usual, as the field matures, the unanswered questions that remain, they are the most difficult, they are the toughest. And so one of the questions that I think needs more work, but needs work by somebody who is really, you know, careful and willing to, you know, understand things deeply, is the nature of the phase transition. This nature of the phase transition is, but this is a problem also, if you want, at some level also for the Anderson model, right? I mean, in the Anderson model, we have the beautiful works on nonlinear sigma models, the epsilon expansion, but then if you try to do the epsilon expansion and you put epsilon around dimension 2, you put epsilon equal to 1, you get critical exponents which don't mean anything. So even, I mean, the critical point of the Anderson and MBL transitions are still big mysteries. Of course, MBL is going to be much tougher to solve. But, you know, a young, ambitious theoretical physicist might want to tackle these kind of things.
I have another question coming back to these integrals of motion. So you mentioned that the local ones should scale as the volume, right, of the system?
Yes, they do. Yes.
But then on the other side, there was the saying that the many-body localization or the transition from metallic to this many-body localized phase is nothing but Anderson localization in Fock space. Now, if I do go into Fock space, then I would say if I now replace my whatever real space by Fock space side, so to say, then I would expect that I need, coming back to what Ihors asked, I need not, I need local integral, I need integrals of motion basically, which scale as the, I don't know how to call that, the volume of the Fock space or whatever, the number of states in the Fock space.
So let me, so it depends how you define Fock space. Okay, so if you define Fock space, for example, take the spin chain. What is the spin chain? Take this spin, okay? if you look at the hypercube made of the basis SZI, okay, then you look at the an eigenstate in this hypercube. This hypercube has 2 to the n dimensions, 2 to the n vertices, okay, and connectivity n. From every point, you can flip n spins and go to another. If you look at an eigenstate of this system with disorder 10, okay, this eigenstate is not localized on Fock space. No. If you look at the participation ratios, they will tell you that it doesn't take a finite fraction of Fock space, but it doesn't take an order 1 sites. It takes a number of sites which grows exponentially with n, but with a smaller exponent than log 2. So this was already investigated in 2013 in a paper by myself and Andrea De Luca, who was a student of mine at the time. So there is no localization in Fock space. Of course, if you define, if you define your state as your space as the space of eigenvectors, there are 2 to the n of them. Every eigenvector corresponds to one site, it's localized. But there is no, because there is no natural definition of Fock space. It's a fiction of the mind. It's something.
I just take a product state of the non-interacting.
Right, the sigma, the SZs. If you do that, okay, right. But then there is no localization in that basis. The MBL is not a transition of localization in that basis.
Okay, but when the interaction is 0, then all the Fock states are nice eigenstates.
Yes, but as soon as you turn on the interaction, then the participation ratios grow.
So what happens at an infinitesimally small interaction? What would you think?
You have to scale the interaction with 1 over n. And then because you have, then it becomes the Anderson problem with connectivity n. So if you scale the hopping, which is the interaction with 1 over n, then you are localized. But that's not the MBL transition.
Okay.
That's much more extreme.
Thank you.
Okay, so we also have a short discussion session after maybe 5-10 minutes.
Okay.
So I think we can postpone all other questions to the discussion session if required. So I'd like to thank our speaker once again for this wonderful talk. Thanks, Antonello.